Okay. The next topic is classification of magnetic materials. For this classification, we have the terms. First term is a magnetic intensity. Magnetic intensity, that is equal to, magnetic intensity is H. Field that we have to apply for the magnetism is called magnetic intensity, and it is the ratio of B naught upon mu naught, and it is measured in ampere per meter and oersted. That is the older unit for measuring this magnetic intensity, H. And it is also called H field or magnetizing field. This is the first. And second is intensity of magnetization. Intensity of magnetization. The material, after applying this intensity, how they get magnetized, that is I. And this is dipole moment upon volume. Magnetic dipole moment upon volume. It is again measured in ampere per meter. And in another form, this is written as 2L. This is volume is written as this. So M by A. This is also called the magnetic intensity. It is also measured in ampere per meter. Then we have the third term, that is magnetic flux, means the number of field lines passing through the surface normally, and this is the B dot ds vector, and its SI unit is called Weber. And the fourth is magnetic induction. These are the terms that we have to use for the classification. Magnetic induction, that is written as the sum of applied field and magnetized field, mu naught I, that is equal to this mu naught. If we put here H, mu naught I, it become mu naught H plus I. So this is the magnetic induction. This is existing field and this is magnetizing field. The sum of this is called magnetic induction, measured in Tesla or Weber per meter square. If we have to draw this diagram, now this is the magnetic field, that is B naught, and we place a magnetic material bar magnet shape that is magnetized in this field, and these lines are its magnetic field. After this, when we got this combination, we get this result. So these field lines, they are opposite to this applied, so they neutralize, means there is some less of field, but here these field at the point of ends, they support the field, so here large field. So this combination, that will be give this value, that is called magnetic induction. And the susceptibility, that is the chi m, magnetic susceptibility, the ratio of intensity of magnetization to magnetic intensity, I upon H. No unit, it is a unitless quantity or number. And the term sixth is called magnetic permeability, that is B upon H, that is a magnetic field and magnetic intensity, and it is Tesla meter per ampere. And the term mu upon mu naught, that is called relative permeability. So these are the terms that we have to use to classify the materials. And the relation, how we find the relation, that is B is equal to mu naught H plus I, divide both sides with H. And when we divide both sides with H, what we got here, 1 plus I by H, this is B by H, that is mu, and when mu upon mu naught, 1 plus chi, and this is called mu r, that is 1 plus chi m. This is the relation for that. And on the behalf of these materials, terms, classification, material is classified into the three categories, that is diamagnetic, then paramagnetic, and then ferromagnetic. Diamagnetic materials are those which are feebly repel, less magnetism. They are feebly attract. paramagnetic, and they are highly attracted towards the magnetic field that is ferromagnetic. And their behavior, they always move from, if they are placed in non-uniform magnetic field, always move from stronger to weaker part, but they are moving from weaker to stronger part. And their behavior is temperature independent, but their behavior is temperature dependent, and their behavior become temperature dependent after a certain temperature. So there are some properties for describing this, but for this we have electron theory. To describe this magnetism behavior, we have the electron theory. Now this diamagnetic, that is non-magnetic, we can say, that is repelled by the magnetic field, feebly repelled by the magnetic field. It, according to this electron theory, diamagnetic materials first in atoms, the dipole moment is minus E upon 2me L vector, opposite to each other. And according to this theory, in diamagnetism, paired electrons are exist, no unpaired are exist. And when the paired electron, they are revolving, we have this diagram. Let's say in pair, one electron is revolving clockwise and the second is revolving anti-clockwise. And for clockwise, this velocity, this angular momentum is downward and the dipole momentum is upward. And here the opposite. So the net dipole moment is 0. But when the magnetic field is applied, in the both cases, in the magnetic field that revolving in anti-clockwise, that will be decrease the velocity and decrease the angular momentum, and which revolving clockwise, it increase the velocity and increase the angular momentum. In the before applying the magnetic field, the both paired electrons have the net dipole moment 0, but after applying the magnetic field, they acquire the net magnetic dipole moment, that is minus 2 delta m vector, that is opposite to the applied field, and that behavior is called the diamagnetism. And for paramagnetism, on the basis of electron theory, in paramagnetism, the materials, they have the dipole moment, but they are randomly oriented. So the net, these are the magnetic dipoles, arrows are the magnetic dipoles, so their net magnetism is 0. But when the field is applied, this field try to align these dipoles in its direction, but it is a temperature dependent substance, and the temperature saturation temperature disturb this alignment. So when at a given temperature, saturation is occur for a particular temperature play an important role here, and the material become magnetized. And the ferromagnetism, on the basis of this electron theory, it is also considered as a domain theory. Means the ferromagnetic materials, they are in the form of small domains where the magnetic materials, magnetic elements are lying in same direction. Each domain, that is a small volume but contain the large number of magnetic dipoles, has the dipole moment, but the net dipole, again the ferromagnetic, is a 0 in the absence of any field. But when the field is applied, this domains, these are, if the external field is very strong and the material is homogeneous and pure ferromagnetic material, then all the domains aligned in the applied field instantaneously and material become magnetized. And one more method to magnetize it, that the domain which is in the direction of applied field, that will be aligning it at the behalf of others. It start aligning to the applied field, and at last the whole material become magnetized. So on the electron theory basis, diamagnetism, that is the unpaired electrons, and paramagnetism give the saturation at the particular temperature, and ferromagnetic, that will be have the domain forms, and the applied field will make the materials magnetized. Here in magnetism we have the one more, that is the Curie law. Curie's law. This law is defined for the paramagnetism, because paramagnetism materials, they are temperature dependent. According to this, for paramagnetic material, before the saturation, the intensity is proportional to magnetic intensity, inversely proportional to temperature. So I is proportional to H upon T, and the constant I is CH upon T. And if we write I upon H, C upon T, and this I upon H is called the chi, C upon T, the constant chi m is proportional to 1 by T. This is called the Curie law of magnetism, where the susceptibility is inversely proportional to the absolute temperature, and the Curie temperature is defined for ferromagnetic material, where at above this temperature the ferromagnetic material loses its ability to magnetized. Then we have the properties of these materials. For diamagnetic materials, feebly repel, and if it is a bar if a rod of diamagnetic is, this is north south applied field, magnetic is suspended in this, it always lying in perpendicular direction, and for para and dia, they are in the directions. And if the materials, they are placed in a non-magnetic field, the dia is always moving from a strong to weak field. And for the diamagnetic, the I value, the value of intensity, is a small negative value. For para it is small positive, and for ferro it is a very very large value. And when it is very important property, north south, if the diamagnetic material is placed in this, the field lines, they are away from this material, but if paramagnetic is placed, field lines passing through this, and if the ferromagnetic is placed, the field lines try to passes all the field lines passing through the materials. And this chi m is negative for diamagnetic, positive for para and ferromagnetic, and these are the properties which are used to differentiate these materials. And then we have this hysteresis. Hysteresis means the lagging, and this property is shown by only the ferromagnetic materials. This is the variation of I and H. By giving the material H, then the intensity of magnetization that will be acquired lagging behind is called hysteresis. For that, we have this hysteresis curve. If we have this H and this is the I, we start to magnetizing, materials start magnetized. By giving the H up to point A, it becomes saturate, and above this no magnetism is exist. Then we demagnetize the material, but the curve take the another path, that is AB, and here the applied field becomes 0, but the material retain this amount of value, that is called retentivity of the material. And to make it 0, the field is applied in opposite direction, and this value which is applied in opposite direction to make the intensity 0 is called the corrosivity. And here again the saturation, again, that is minus means opposite direction. Then again we have retentivity, and then again corrosivity, and finally the magnetization curve is complete. So The retentivity is the value of intensity of magnetization. When the applied field becomes zero, the amount of field retained in the material is called retentivity. And the corrosivity is the value of applied field in opposite direction to make the material unmagnetized. And the material which are going from magnetism, unmagnetism, again follow this curve, and the area of this curve is equal to the loss of energy, that is that will be appear in the form of heat when the ferromagnetic materials undergo repeatedly magnetism or demagnetism. On the basis of this hysteresis loop or curve, we should differentiate the materials and select the materials for the different purposes. If we have the curves, this is for hysteresis curve for soft iron and the hysteresis curve for steel. Then if we differentiate them, these two curves, if we differentiate, the area of soft iron is small, so this is used to make the electromagnets, temporary magnets which are undergo magnetism and demagnetism. Its retentivity is large, so it becomes strongly magnetized, and corrosivity is small, so it is easily demagnetized. Area is also small because it undergo the magnetization circle. And for the steel, the retentivity is large, but the corrosivity is also large because it's used to make the permanent magnets. Its area is large, but for permanent magnets, this is not used for the magnetization or demagnetization. So on the basis of this, the materials are classified and for the different uses. Okay ji, thank you.